Welcome to the final learning outcome on the pressure and flow of fluids. We'll look at how pressure behaves in fluids that are standing still and in fluids that are moving, and meet the key laws that govern both. Let me lay out the plan. We'll start with how pressure acts inside a static, still fluid, then move on to how pressure and flow behave once the fluid is moving. Along the way, we'll meet three key laws, Pascal's, continuity, and Bernoulli's, and see them at work in real devices like siphons and hydraulic lifts. And as ever, we'll solve numerical problems and get into the habit of stating the principle we're using each time. Let's begin with a simple question. What is a fluid? A fluid is anything that flows, that means both liquids and gases. Fluids take the shape of whatever container holds them. We call a fluid static when it's at rest and dynamic when it's moving. One important difference, liquids are almost incompressible, so you can't really squeeze them into a smaller volume, whereas gases are compressible. Engineers spend a lot of time controlling fluids, in hydraulics, in pipelines, and in pumps. Let's settle the key terms. Pressure is the force acting at right angles per unit area, measured in pascals. Density, or ρ, is mass per unit volume, mass over volume, in kilograms per cubic meter. Head is the vertical height of a column of fluid, measured in meters. A static fluid is one at rest, not flowing, while a dynamic fluid is one that's moving. Keep those last two straight, because the method you choose depends on which you're dealing with. Let's define pressure properly. Pressure is the force acting at right angles to a unit of area, and it's simply force divided by area, measured in pascals. 1 pascal is 1 newton per square meter. Spread the same force over a larger area and the pressure drops, which is why a sharp point concentrates pressure and a broad base reduces it. And here's a feature special to fluids. In a static fluid, the pressure acts equally in all directions. Let's do a quick calculation. A flat plate of area 0.05 square meters carries a force of 200 newtons, acting at right angles to it. And we want the pressure. Pressure is force over area, so 200 divided by 0.05, which is 4,000. So the pressure is 4,000 pascals, or 4 kilopascals. Now let's see how pressure grows with depth. In a static liquid, the deeper you go, the greater the pressure, and the formula is pressure equals ρGEH, that's the density, times G times the depth. Here, G is 9.81 and H is the depth below the surface. Notice the pressure depends only on the depth, not on the shape of the container at all. It's exactly this that explains why a dam wall is built much thicker at its base, where the water pushes hardest. Let's find a pressure at depth. What's the pressure 3 meters down in fresh water, taking the density as 1,000 kilograms per cubic meter and G as 9.81? Using pressure equals RHOGH, that's 1,000 times 9.81 times 3, which multiplies out to 29,430. So the pressure is about 29,430 pascals, or roughly 29.4 kilopascals. Let's connect pressure with the idea of head. Rearranging pressure equals ρGEH gives the head H, as pressure divided by ρg. Head is just a way of expressing a pressure as an equivalent height of fluid, which turns out to be very handy when you're designing pumps, tanks, and water supplies. For instance, that 29,430 pascals we just found is the same as 3 meters of head in water. It's why a tank mounted higher up delivers greater pressure at the tap below. Let's meet Pascal's law. It says that when you apply pressure to an enclosed fluid, that pressure is transmitted equally and undiminished throughout the whole fluid. For it to hold, the fluid needs to be enclosed and effectively incompressible, which liquids are. This is the principle behind every hydraulic system you'll come across. Car braking systems and workshop jacks both rely on Pascal's law to carry pressure from where you apply it to where you need the force. Let's see how Pascal's law gives us force multiplication in a hydraulic lift. two pistons are connected and share the same fluid pressure, so the pressure equals the force on the small piston over its area and equally the force on the large piston over its area. Rearranging, the output force is the input force times the ratio of the two areas. So a large area piston produces a much larger force, which is how a small push at one end lifts a heavy car up on a ramp. Let's put numbers to it. A small piston of area 0.01 square meters is pushed with 50 newtons, and the large piston has an area of 0.02 square meters. What's the output force? First, the shared pressure, force over area on the small side, 50 divided by 0.01, which is 5,000 pascals. Then the output force is that pressure times the large area, 5,000 times 0.02, which is 1,000 newtons. So 50 newtons in gives 1,000 newtons out, a 20-fold gain in force. Let's look at the siphon, a rather elegant device. A siphon moves liquid up and over a barrier without any pump at all. You first have to fill the tube with liquid to get it going. Then, as liquid falls to the lower outlet, it pulls more liquid up behind it, and the flow keeps itself running. What drives the whole thing is the height difference between the two ends, helped along by pressure. It's how we drain tanks, ponds, and aquariums. Let's pause and check. First, why does pressure increase with depth in a static liquid? Second, can you state Pascal's law in your own words? And third, how does a hydraulic lift manage to produce a larger output force than you put in? Have a think before we move into flowing fluids. Now let's set the fluid moving. Once a fluid flows, an internal friction opposes that motion, and we call that resistance viscosity. Thick fluids like oil and syrup have a high viscosity, while thin fluids like water and petrol have a low one. Flow itself comes in two characters, smooth and orderly, which we call laminar, or chaotic and swirling, which we call turbulent. Knowing which you've got matters a great deal in real pipe and pump design. Let's define the flow terms. Viscosity is a fluid's internal resistance to flowing. Dynamic viscosity, mu, is a measure of its shear resistance in Pascal seconds. And you'll also hear it called absolute viscosity, which is just another name for the same thing. Volume flow rate, Q, is the volume passing a point each second, equal to the area times the velocity in cubic meters per second. And continuity is the idea that mass is conserved, so that flow rate stays constant along a pipe. Let's compare low and high viscosity side by side. A low viscosity fluid flows easily and quickly, with only small internal friction, and needs very little force to shear it. Water, petrol, and air are good examples. A high viscosity fluid flows slowly and thickly, with large internal friction, and takes much more force to get it moving. Think of engine oil, honey, or syrup. It's really just a measure of how reluctantly a fluid flows. Let's look at the continuity equation. For an incompressible fluid, the volume flow rate stays constant along a pipe, so the area times velocity at one point equals the area times velocity at another, remembering that flow rate Q is area times velocity. The consequence is intuitive. Where the pipe narrows, the fluid has to speed up, and where it widens, the fluid slows down. At heart, it's simply an expression of the conservation of mass as the fluid moves through the pipe. Let's work a continuity problem. Water flows at 1.5 meters per second, where the pipe area is 0.02 square meters, and the pipe then narrows to 0.005 square meters. What's the new speed? Continuity says area 1 times, velocity 1 equals area 2 times, velocity 2. So the new velocity is area 1 times velocity 1 over area 2. That's 0.02 times 1.5, which is 0.03, divided by 0.05, giving 6 meters per second. So the flow speeds up from 1.5 to 6 meters per second as the pipe narrows. Now for Bernoulli's equation, which ties together pressure, speed, and height in a moving fluid. It states that the pressure plus a half RHO-V squared plus RO-GEH stays constant along a streamline. It assumes steady, incompressible, frictionless flow. The striking consequence is that where a fluid speeds up, its pressure falls, which can feel back to front until you're used to it. And underneath, it's really nothing more than the conservation of energy applied to a flowing fluid. Let's contrast the static and dynamic cases. In the static case, the fluid is at rest, its velocity is 0, and the pressure is set purely by depth, ROGH, acting equally in all directions and governed by Pascal's law. In the dynamic case, the fluid is moving, so its velocity is greater than 0, and now speed and pressure are linked by Bernoulli. Faster flow means lower pressure, while the flow rate itself is fixed by continuity. Recognizing which case you're in tells you which law to reach for. Let's apply Bernoulli in a horizontal pipe. Water of density 1000 flows along a level pipe. At point 1, the pressure is 200 kilopascals and the speed is 2 meters per second. At point 2, the pipe narrows so the speed rises to 6 meters per second, and we want the new pressure. Because the pipe is level, the RHO-GH terms cancel, leaving pressure 2 equals pressure 1 plus a half, RHO times V1 squared minus V2 squared. Substituting, that's 2,000 plus a half times 1,000 times 4 minus 36, which is 2,000 plus 500 times minus 32, or 2,000 minus 16,000. So the pressure drops to 18,400 pascals, that is 184 kilopascals, as the speed rises. Let's see where Bernoulli turns up. It explains the lift on an aircraft wing, where faster moving air over the top gives a lower pressure. It's behind the Venturi meter, where a deliberate pressure drop lets you measure the flow rate. Carburetors and spray guns use fast-moving air to draw fluid in, and a pitot tube uses it to measure an aircraft's airspeed. And whenever you solve one of these, get into the habit of naming the principle you're applying. Let's check your understanding. First, in continuity, what happens to the speed when a pipe narrows? Second, why does the pressure fall where a fluid flows faster? And third, which conservation principle does Bernoulli's equation express? Have a think about each one before we finish. Let's finish by choosing the right method for the job. For the static pressure due to depth, use pressure equals ROGH. For a force in an enclosed fluid, use Pascal's law together with pressure equals force over area. For a change of speed in a pipe, use continuity, area 1 times velocity 1 equals area 2 times velocity 2. And for the link between pressure and speed in a flow, use Bernoulli's equation. Whichever you pick, state the principle clearly and always check your units.